Hi guys, Tim's back again. Today I'm going to talk to you a little bit about, this is for my lovely A2 students. I'm going to take you a bit further forward and I'm going to give you some work on, show you a little bit about carbon-13 spectroscopy, how it works, and then use carbon-13 spectroscopy to introduce you to proton spectroscopy, which is the last major topic really that I need to teach you. There's a few little bits and bobs, but we can sort that out later. Carbon-13 spectroscopy, proton spectroscopy is a big deal, so we need to be absolutely spot on and sorted. So the first thing we're going to do is carbon-13 spectroscopy. Okay, now there's some of the worksheets that I'm going to be using I can email to you, so don't worry about it, so you can have a go at this yourself and learn the basic principles of it and what's going on. Okay, I know it's a bit of a mess in here, but we'll do our best, okay? Right. Okay. Carbon-13 NMR spectroscopy. Okay. Now, first thing, there's a number of things. This is a non-destructive technique, so you can take your sample and it doesn't ruin it, it doesn't spoil it, you can use it for other things. That's the first thing. The intricacies of how it all works we don't need to know about, but we do need to be able to interpret things. Now you take your sample, and first thing you've got to do is dissolve it in a solvent. Now the solvent has implications which we need to look at a little bit. Let me explain what I mean by that. Right, the solvent that we use is this stuff here. Trichloromethane. Right, but as you will see, there's a bit more to it than that. Trichloromethane, CH3, CH, there, that's trichloromethane, no problem at all. Let's make sure I get out the road. Right. It's unbelievable. Right. Okay. Now, what we do is, this proton here, as you will see later, is going to be picked up in our proton spectroscopy. This solvent is used for carbon-13 and proton spectroscopy, but it's got a proton in it and we don't want it to interfere with the sample that we're going to look at. So what we do is we deuterate it. Okay. Now deuterium is this. That's ordinary hydrogen. No neutrons. That's deuterium, one neutron. And this is tritium. I believe it's the only isotope that you've got three different symbols for three different isotopes. Very, very famous isotopes. Okay, now, if we deuterate, we replace our ordinary protons with heavy protons. These are the protons that are in heavy water. Heavy water is D2O. Or I believe T2O even. It's actually heavier, but it's exactly the same as water. You wouldn't see it. Looks like water. You can have a bath in it, whatever, but highly radioactive. And it's heavier because each particle has got one more neutron to it. So it's pretty cool, really. And that is what we're going to use. So what we use is deuterated trichloromethane. So by some process, the protons are replaced by deuterium. And that is our solvent that we use to dissolve things in. Right there, okay? No protons to be picked up. Yeah, there's a carbon, but we can deal with that, that's fine. No protons to be picked up, so everything can be dissolved in that and it doesn't interfere with what we're trying to do. Okay? Okay guys, sound. Right, so carbon-13 NMR first. What it does is identified. You must make notes on all this. This is for you to write down. So it identifies different carbon environments. Okay, so let's have a look. What do you mean by different environments? Well, I think first of all, I'll need to refer you to this data sheet. You get one of these in the exam. That's for your proton NMR spectroscopy there. But the principles are the same with carbon. If a carbon is double bonded to an oxygen, you will get a peak in this chemical shift region. The chemical shift depends what the carbon is joined to and shifts according to that. So C double bond O, a peak will occur somewhere there. Aromatics, or C double bond C, will occur there. C single bond O will occur in this chemical shift region. CN, CC, obviously very common down the bottom end, and you've got your halogens there. That's all you need to know. So we'll try and keep that in mind all the time. Right, so let's have a look at our first one. I think it might be best if I do a thing. Okay, so let's have a look. Perhaps I should have done it a bit lower. It's hard to gauge really. Anyway, okay then. So guys, let's have a bit of a look at this. Let's have a look at our first molecule that we're going to analyse and do a proton spectroscopy on. Excuse me while I faff about here. Okay, so I'll try and keep this here. C. All these questions are on a pack. The pack I'll show you later. The pack I'll email to you. No problem. So we're going to look at propan 1-ol. There it is. How many different environments? Carbon. Not interested in the protons, I should keep saying that. Well, you've got a carbon joined to a carbon here, which appears to be at, let's have a look at my sheet, somewhere between 0 and 50. That one there, somewhere between 0 and 50, CC. Okay, if you look on your data sheet. Now, if you look at that one, looks very similar, CC. But is it identical to that? You'll see about this equivalence, this sort of idea of symmetry later. No, because that C is a part of a methyl, that C is sort of in the middle with two H's on it. They're not the same. Second environment. It'll be close, but it won't be exactly the same. This will be illustrated much more later. And this one, definitely different. Here you've got a C joined to an O. So what we've got here is a couple of slightly different peaks, CC for 1 and 2, and this C joined to an O, there'll be a peak up here, C joined to an O. 3 different environments, 3 different peaks, each with a different chemical shift. Okay, so let's see. Easy. Absorption. Always. Chemical shift now goes up to about 220. So 100, 200, 0. I'll use this for others. 50, 150, so on and so forth. I don't want to get too carried away. Right, so let's go to red here, guys. Let's get it sorted. Okay, I hope you can see all right. Let's go to red. Where are these peaks? 3 different environments. Get your chemical shift out, no problem. Doesn't matter about where these two go as long as they're separate. 3 different environments, 3 different peaks. That's about as much as you need to think about on this. So, answer. 2 between 0 and 50, that, and 1 between 50 and 90. Okay? In other words, I'm not too bothered about where these two appear. Okay, so in other words, 2 between 0 and 50. Never mind the height, 2 there. And 1 between, call it, say 70 odd there. That is essentially the carbon-13 spectrum for that molecule. That is definitely CO. That's number 3. It complies to the chemical shift on your data sheet. That is, say, 2. That is, say, proton number 1. Okay, there you go. 3 different environments, jobs are good. Okay, I'm going to stop the video and start another one because I want to see if this has worked all right, do you know what I mean? Because I don't like to do this for hours and find out it hasn't. Okay, guys, so I'll catch you shortly. There'll be one straight after this, following on from exactly this point. Cheers, thank you.